So, of course, this integral is straightforward to evaluate using the antiderivative of inverse tan, but we'll see what happens when we try and do it using the residue theorem. So, for an integral of this type, our contour will be the semicircular one, going from minus r to r. Always good to label your axes, explain what you're doing. So we consider the integral around the contour gamma of dz a squared plus z squared. So, and in the limit as r tends to infinity. So, what do we get? Well, as r goes to infinity, this part of the line integral along here will be precisely the integral we want. So that's the first bit there is just I. Then we've got the integral around here. This is the one we have to consider and show that it actually goes to 0. So it's the limit as r goes to infinity of, so what have we got here? So around here, on this semicircle, we have that z is equal to r e to the I theta. Okay, so a general point here we call theta. So that means that on here, dz is equal to r times e to the I theta times I d theta. So we end up with dz is now r e to the I theta times, differentiate this, I d theta. And on the bottom, we have a squared and r is, z is r e to the I theta. So that's squared, so you got this thing on the bottom. And theta is varying from 0 up to pi. So all we have to notice is that we've got r divided by r squared as r goes to infinity. So basically, this is going to end up being of order r to the minus 1, which we can say is going to tend to 0. Okay. So we have now that the integral we want, I, is equal to this contour integral. What we haven't done yet is show where the poles of this are. So this has poles at, okay, well, if we want to factor it, I guess we can factor it. So z squared plus a squared is z minus ia times z plus ia. So it has poles at ia and minus ia. So the only pole we're interested in is the one inside the contour. So we now have that I, by the residue theorem, is 2 pi I times the residue of the function we're considering, 1 over a squared plus z squared, evaluated at z equals ia. So now we're good at doing residues. This is p over q. So we want p over q dashed. So we end up with 2 pi I times 1 over, and then differentiating this gives us 2z, so that's 2 ia when we substitute in z equals ia, which gives us pi over a as expected. As a check, notice the dimensions are correct. So this is dimensions meters, this is meters squared on the bottom, so we expect to get 1 over meters as the final answer. Also, obviously, this is a real positive integral, and this is also real and positive. We're assuming a is greater than 0.